the last of the three special case transmission lines that I want to look at is the case of the open circuited lossless transmission line. And for an open circuit, the situation that we've got here is that the resistance across the load is equal to infinity. And there's two observations that we can make here. First is that the load current has to be equal to 0. No current can be flowing through there. And then the voltage across this, we don't know what its value is, but the voltage at the load is going to be some maximum value. Right? It won't be 0. It's going to be whatever the full output voltage at the ends of the transmission line are. So to analyze this situation, what we want to do is we want to go back to our equation that the voltage, the phasor voltage along the length of the transmission line is equal to whatever the magnitude and phase shift of the incident waveform is, or the incident voltage wave is, times e to the minus j beta z plus whatever the reflection coefficient is at the load, e to the j beta z. So in this case, the reflection coefficient at the load is equal to infinity minus 0 over infinity plus 0, or plus z0, excuse me. And so that's going to give us infinity over infinity, which is equal to 1. And so we can just put the reflection coefficient of 1 is equal in here, and so that gives us equals v bar plus e to the minus j beta z plus e to the j beta z. So that gets plugged in there. And if we did a bunch of math, what we could see is that the magnitude of the voltage along the length of the transmission line for the special case of the open circuit is going to be given by 2 times v bar plus times the absolute value of the, that's magnitude of 2 v bar plus times cosine of beta d magnitude, and something pretty similar looking for the open circuit current as a function of length. The magnitude of that is going to be equal to 2 I bar plus times the magnitude of sine of beta d. And again, we're just plotting magnitudes here. That's not the actual value of the current, or the voltage in the current, it's just the magnitude of it. So if we were to plot those, we'd see that the magnitude of 2 v bar plus here follows, again, this cosine term. So cosine terms are 1 at length equals 0. It's going to be 0 when beta is equal to lambda over 4. Or sorry, when d is equal to lambda over 4. It's going to go back to a maximum here, a minimum here, a maximum here, a minimum here, a maximum here. We're going to get this shape like this, where these are rectified sine waves. So, I'm not the best sketcher, but those are rectified sine waves. And we see that relationship there holds true to the fact that this has got to reach some sort of maximum value. The voltage has to reach some sort of maximum value at the load. And then if we were to plot this for current, we get the magnitude of 2 I bar plus. And at the load, it's going to have to be 0. And this equation, again, says that it is. So we're 0 here, and we're the amplitude of it is maximum at lambda over 4. We're back to 0 at lambda over 2. We're back to 2 times I bar plus here, etc. So this is going to look like this. All right, so we've got a voltage and a current waveform that are out of phase here. If we were to plot the Zn, again, it's going to just be voltage divided by current, and these are magnitudes, so we're going to have to take some liberties with the plot here. But if we were to plot those, we'd see that at the load, the input impedance is going to be negative infinity. It's going to go to 0 at lambda over 4, and then it's going to go to positive infinity at lambda over 2. So we get this, again, kind of asymptotic behavior that looks pretty similar to what we saw for the short circuit. And this behavior is going to repeat itself every lambda over 2 cycles, where lambda over 4 integer multiples are going to have 0 input impedance, and then at lambda over 2 multiples we're going to have infinite input impedance. And so we've got that plot. And what's that? What is that showing us? Is that over the first quarter waveform from the load, the reactance is negative, and it assumes all possible negative values up until it reaches lambda over 4, where at lambda over 4 from the load, the line appears as a total short circuit. There's no input impedance. As the line length exceeds lambda over 4, the reactance is going to become positive, and it's going to assume all possible values over that next quarter wavelength cycle. Right? At a distance from lambda over 2 from the load, the line appears as an open circuit. Its impedance has gone to infinity, so it appears as an open circuit. So at the load, the input impedance appears as an open circuit. At lambda over 4 from the load, the input impedance appears as a short circuit. At lambda over 2, it appears as an open circuit. And between 0 and lambda over 2, we can make it take on any value of reactance that we want to. And mathematically, this comes from Zn is equal to Z0 times infinity plus J Z0 tangent of beta L over Z0 plus J times infinity tangent of beta L. So that again is I've just plugged in ZL is equal to infinity for the input impedance equation. And so that's going to give us Z0 times infinity over J infinity tan beta L. My infinities are going to cancel. That gives me Z0 over J tan beta L, which is just equal to minus J Z0 cotangent of beta L. And that's the input impedance for the special case of a open circuit. And this is showing us that we can use a transmission line that's been open circuited to also create a reactive element of any value that we like. Big point, this is purely imaginary, right? So we'll see applications of that in a couple classes.